Okay, so now we're on to statistical backtests, and I'm going to go over that binomial distribution that we looked at in the previous video in a few more details. So many of you will already understand this, of course, but just to recap, probability P or pi in this case, or alpha in the previous video, that's the probability. Suppose you've got a coin that's unfair, so the probability, call it pi, of getting ahead is something like, say, 0.3, more likely to get a tail. And if you flip this coin 10 times, you're interested in the number of heads you get. That's an example of the binomial distribution, which is the number of successes in 250 or some number n of independent trials. And each time there's the same success probability. So in this case, we could say x is distributed as a binomial with n equals 10 and the probability is 0.3. More generally, we would say x has the distribution b n pi. N is the number of trials, and in backtests, the n would be the number of days that you do the backtests for, and pi is the probability of success, and in the backtests, it will be alpha, the quantile level for the risk model. So the binomial has a likelihood function, which is another term just for the height of this density. Don't forget it's a discrete density, so it doesn't look like a curve. It looks like a series of nails, a series of spikes, right? And the height is called the likelihood, and this formula gives you the likelihood, the probability of getting exactly k successes in n trials is given by this combinatorial coefficient, nk, which is n factorial over k factorial times n minus k factorial, also on the denominator. And here we've got pi to the power k and 1 minus pi to the power n minus k. So you have k successes, each with probability pi. That's the probability that the number of successes equals pi. And then if you've got n trials and you've got exactly k successes, then you must have n minus k non-successes with probability 1 minus pi. So that's why you multiply it. And then the number of ways in which you can get k successes and n minus k non-successes. I mean, then the ordering matters. You know, you could have it on the first k trials, they're all success, and then all the rest are not success. Or there can be a different type. So that's where the combinatorial coefficient comes in. It's the number of ways in which you can get k successes in n trials. And this exclamation mark is called the factorial. So n factorial is n times n minus 1 times n minus 2. In other words, it's like 6 times 5 times 4 times 3 times 2 times 1. That's 6 factorial. Anyway, so as I stated in the previous video, a binomial variable has mean n pi and variance n pi 1 minus pi. So if pi is 0.3, then the variance of where there are 10 trials is 10 times 0.3 times 0.7, which is 2.1. And here's another numerical example. What is the probability that x equals 3 if we have 5 trials with success parameter 0.4? So we do 5, 3, 0.4 to the power 3, and 1 minus 0.4 to the power 5 minus 3, using that formula. Calculating the 5, 3 binomial coefficient, we get 10, and then we can calculate the probability that x equals 3 as 10 times 0.4 cubed times 0.6 squared, which is 0.2304. Right, so why was I doing all that? Well, because likelihood ratio tests are the best way to properly test an internal model. And although banks have to pass the test for regulatory purposes, banks also use these more sophisticated back tests because it's not just for regulatory purposes. They want their internal model to be accurate. They use their internal model for the allocation of what we call economic capital. using risk-adjusted return on capital. So the risk bit is where they'll use the internal model to come up with an accurate risk estimate. And it's not just the banks that use these statistical backtests. For example, exchanges, the central counterparties, CCPs, they have to have very rigorous models for determining what the margin should be for their client's position. And that model is also backtested using, because it's basically a VaR or ES type model. It's the same type of model. A normal model may not be very good though, but historical or exponentially weighted moving average normal models, where instead of just an average standard deviation for the sigma, you use a UMA. That's very popular as well. So these more sophisticated models that are used not just by central counterparties, but also banks and investment firms. This is the backtesting framework that they adopt, and it's based on a likelihood ratio test. So what is a likelihood ratio test? It's a test to see whether the observed data fit the data that we expect under a particular model. So it's the ratio of L0, which is the expected maximum likelihood under the model, and L1 is the observed maximum likelihood from the data. And the LR test statistic is the ratio of the two, we call it lambda, but because these likelihoods are products, so the likelihood of data is the likelihood is the height, right? And to get the likelihood of a whole sample, you have to multiply lots of heights together. And so multiplication is difficult in terms of like finding the maximum. You have to differentiate. So instead of using the actual likelihood, we prefer to use the log likelihood, because that turns a product into a sum, and it's easy to differentiate a sum. And anyway, if we take minus twice the log of it, then we can show that that has a chi-squared distribution, and it has certain degrees of freedom, which I'll talk about when I look at these tests in more detail as they pertain to the back tests of value at risk. So remember, the log turns a ratio into a difference, so the minus twice log lambda is minus 2 times the log of L0 minus the log of L1, and it's that's our test statistic, okay? So the statistical backtests were introduced, in fact, by somebody, Paul Kupiec, from the Federal Reserve in the US in 1995, and then made more sophisticated by Peter Christopherson in 1998. And the null hypothesis is that this exceedance process, remember the 0001, 00110, that process, the null hypothesis is that it has success probability alpha. In other words, the model is accurate, okay? So the test statistic is the ratio of the expected proportion of exceedances according to the model and the observed proportion of exceedances that you actually see in that process. So in the numerator here for the test statistic, the pi x is alpha. It's just what the model, what the expected proportion is according to the model. And if it's an alpha percent VaR model, then it would be alpha for pi x. So you can read this top thing here as alpha to the power n1 times 1 minus alpha to the power n0, where n1 plus n0 is the size of the backtest sample. So n1 is the number of ones, n0 is the number of zeros, and the two together, n1 plus n0, makes n, which is the backtest sample size. But it may be that the proportion of exceedances you get is not 1%, it's 3% or something like that. So pi obs is the observed proportion of exceedances that you actually get in your back test. And then the degrees of freedom is 1, so minus 2 log of this LR. We call this the unconditional coverage test. This is the simplest one. And so minus 2 log LR has a chi-squared distribution with 1 degree of freedom. So here's an example. A back test of 2.5% VaR with a sample size 500 yields 20 exceedances. Perform an unconditional coverage test on these results, given that the 1% and 5% critical values for this chi-squared distribution with 1 degree of freedom are 6.6349 and 3.8415. So those are our critical values. So we've got to calculate the statistic LR, you see, using pi x is 2.5%, so that's 0.025 for pi x. And how many exceedances were there? Well, there were 20 exceedances out of 500, so pi obs is 0.04. And so the number of exceedances is 20, and it was 500 observations, so that's 480 non-exceedances. And so we have to calculate this ratio here. And actually, my calculator didn't explode, even though with larger numbers it would have, or smaller numbers on top here or on the bottom. I mean, 0.04 to the power of 20 is something very, very small. Anyway, I managed to calculate it. It's 0.141132, and then taking minus 2 log of 0.141132, I get 3.916, which just exceeds the 5% critical value of 3.8415, but not the 1%. And so there is some evidence that it fails, but it's not failing at 1%, it's only failing at 5%. We should also perform back tests for significance levels other than 2.5%, like 1% as well, and using obviously different portfolios, different samples. And I mentioned a calculator problem. Because you've got something small underneath, like here, we've got 0.04 to the power 20 in this, you may have a real problem. And so you can always do it differently. You could calculate minus 2 log LR as the log of the top minus the log of the bottom. And that would be, actually, you could even break the log of the top into n1 times the log of pi x plus n0 times the log of 1 minus pi x. And you can break up the bottom as well using the property that the log converts a product to a sum and a ratio to a difference. So then you can easily compute these different tools. So if the internal model is accurate, exceedances are not going to come in clusters. And that's one of the real problems. You see at the end here, you've got a whole wodge of exceedances. It was fine during 2003, 2004. There were no exceedances at all. But then towards the end, there are loads and loads of exceedances, and that's going to erode the bank's risk capital if its capital requirement goes up and up over all those exceedances. Or if the risk is, if it's an investment firm, it could be losing money day after day on its positions. So, because its P&L is so negative. So the independence test is a different test where you've got a more complicated denominator. What was in the denominator here, this pi obs n1, 1 minus pi obs n0, now goes into the numerator. And then you have a more you've got something capturing whether a 0 follows a 1 or a 0 follows a 0 or a 1 follows a 1 in the denominator. So pi 0, 1 is the proportion of times that a 0 follows a 1 when you've got when a 1 follows a 0. So Nij is the number of indicator I followed by indicator j. So N01 is the number of 1s followed by 0s. And then the number of the number of 0s followed by 1s. N01 is the number of 0s followed by 1s. N00 is the number of 0s followed by 0s, and N01 is the number of 0s followed by 1s again. So underneath, you've got N00 plus N01 to find the proportion. So N00 plus N01 is N0, the number of 0s. And similarly for pi 1, 1, N10 plus N11 is the number of times a 1 is followed by a 0, and the number of times a 1 is followed by a 1, so that's the number of 1s. And so N11 is the proportion of all the 1s that are followed by 1s, and N01, pi 01 is the number of times a 0 is followed by 1 over all the 0s. Made a bit of a mouthful of that, didn't I? I hope it's clear on the slide. So anyway, this time we've got another chi-squared distribution for -2 log of LR. And so there must be at least one cluster of exceedances for this test to work. Then there's the conditional coverage test, which is a similar sort of thing using the same variables, but you've got the exp on top rather than the obs on top. So actually, if you can calculate this one using the other two. So -2, the LRCC is the sum of the -2 LRUC and -2 LR ind, because you're just switching the top here compared with the ind. The denominator is the same. And this has a asymptotic distribution with 2 degrees of freedom. Okay, so let's do an example by hand. We've got a back test of 1% VaR with 100 observations that yields 20 exceedances. And then there's 3 groups of 2 exceedances that have got zeros, then 1, 1, zeros. There's three of those. There's one time that you get 1, 1, 1. Only once that happens though. There's one group of 4, 1, 1, 1, 1, 1. How many did I say? And the other 7 exceedances, because there's 20 in total, are isolated. You've just got 1 surrounded by zeros. All right, so we've got to compute these numbers N01, N11, and so forth, and N0 and N1. Right. So N is 100, that's the number of observations. 20 exceedances, so N1 is 20, and that means the number of zeros is 80. Now, how many times is a 1 followed by a 1? That's N11. Well, we've got 3 groups of 2 exceedances, so that's 3 times. And then we've got one group of 3 exceedances, and then a 1 is followed by a 1 twice, so that's 5. We've got one group of 4 exceedances, and that's 1, 1, 1, 1. There's 3 times you've got a 1 followed by a 1. So it's 8 altogether, because the other 7 exceedances are isolated. So we've got 8 times that a 1 is followed by a 1, which means, because there are 21s altogether, there's 12 times that a 1 is followed by a 0, because we can get N10 knowing N1 and N11. Similarly, we can count the number of times that 0 is followed by 1 in the same way on your fingers, and it's 12 in this case. And so if N01 is 12, then you must have 68 for n0, 0. All right, so we've got all our n's. And what about the expected proportion and the observed proportion of exceedances? The pi exp, well, or the pi obs, because we can do the independence test, and we can do the clustering test with, depending on whether we use pi exp, or that's for the clustering test, and that's, well, pi exp is 1%. Pi obs is 20 over 100, so that's 2%. No, yes, 20%, not 2%. That's a lot, isn't it? And that's for the independence test. So pi obs is 20%, pi 01 is 0.15, pi 11 is 0.4, and pi exp is 0.01. And then using the calculator or Excel, we get that the independence test, we get a very small number, but for the unconditional coverage test, we get a very large number. And that's because the conditional coverage test, you get a very large number there, because, yeah, that's the effect of having such a small alpha. We need to use chi-squared 2 critical values for the conditional coverage test, which are 0.92103, at 1%, 13.8155, at 0.1%, because we've got such a large value here for the conditional coverage test, it's 91.26. So we rejected at 0.1%, we probably rejected at 0.01% as well. Very obvious rejection of the clustering, no clustering hypothesis there. I won't do the Excel example in this video. I'll do a separate video for going through these tests in Excel. So that's it for now.